Hello and welcome to the second video of Module 6. In this video, we'll be discussing the empirical rule, which is sometimes called the 68, 95, 99.7% rule. Let's get started. A normal curve is a bell-shaped probability density curve. Here's what a normal curve will look like. Notice that it's got kind of like a bell shape to it. Now, normal curves have several properties to them. Here are some of the features of a normal curve. First, normal curves have one mode. You can see that there's only one really tall peak to this curve, so that would be where the mode is happening. Normal curves are also symmetric about the mode. In other words, if we were to fold this curve down the middle, we would see that the two sides would match up perfectly. This is really nice because it then ensures that the mean is equal to the median, which is also equal to the mode. So these three measures of center agree on a normal curve. Now, when you draw a normal curve, it's going to be based off of the mean and the standard deviation. If your distribution has a smaller standard deviation, then your normal curve is going to be tall and narrow. So for example, if I were to have a smaller standard deviation for this normal curve, it would shrink in width and increase in height. This is because, like all probability density curves, the total area under the curve must remain 1. When the data are less spread out, so when the standard deviation is small, the height of the curve must increase to keep that balance. If my distribution is more spread out, in other words, if my distribution has a larger standard deviation, then the bell curve is going to be short and wide. In other words, the curve would sort of flatten out and become much more spread out. Again, it's more spread out because the standard deviation is larger, and if we increase the width, we have to shrink the height to make sure that we maintain a total area of 1 underneath the curve. Let's examine some more properties of a normal curve. As we mentioned before, a normal curve is going to depend on its mean and its standard deviation. Since the mean, median, and mode are all the same, that means that the value that's in the middle of the normal curve is going to be your mean. So I'm going to label on my horizontal axis here the middle value to be the mean. Then you'll notice that I have 3 marks going above that center mark, so 3 tick marks above the mean, and there are also 3 tick marks below the mean. When drawing your normal curve, each of those tick marks is going to be a distance of a standard deviation. So for example, as I move to the right above the mean, I will add 1 standard deviation. Then I'll add another standard deviation to go 2 spots above, and then I'll add another standard deviation to go 3 spots above. As I move below the mean, instead of adding the standard deviation, I'll be subtracting it. So the first tick mark to the left of the center is going to be mu minus sigma. Then I'll subtract another standard deviation to go below, and I'll subtract a third standard deviation to go to the end here. Now I'll point out that I'm using the variables for parameters, mu and sigma, but you could also use the sample standard deviation and the sample mean as well. So you could draw the same curve using an x-bar and an s. Now, since symbols tend to be a little bit confusing, let's do an example just to kind of solidify this idea of how to label this axis. Suppose I had a mean of 33 and a standard deviation of 7. Here's how we would label the axis in that case. The mean of 33 would be in the center. Then, to label up the axis, I'm just going to keep adding the standard deviation for each mark. In other words, on the first space to the right of the 33, I'll take 33 plus 7 to get 40. Then I'll add 7 again to get 47. And I'll add 7 a third time to get 54. To label each of the marks going below, I'm just going to subtract 7 each time. So first I'll do 33 minus 7 to get a 26. Then I'll subtract 7 again to get 19. And then one more time to get 12. So to label the axis of a normal curve, all you have to do is put the mean in the middle, and then you either add or subtract the standard deviation to move each space out. And your normal curve will always look like this, where you have 3 standard deviations going above and 3 standard deviations going below. Most of the data is going to fall within 3 standard deviations of the mean, so this is sufficient for graphing this curve. Let's break down this empirical rule, or the 68, 95, 99.7% rule, a little bit more. To start off with, let's talk about what that 68 represents. So the 68 means if I cut off my normal curve 1 standard deviation below and 1 standard deviation above, I'm going to find 68% of the values. In other words, 68% of my data are going to fall within 1 standard deviation of the mean. For instance, in the example that we're using here, this would mean that 68% of the values would live between 26 and 40 if our values were normally distributed. From the picture, you can see that the shaded region is a little bit more than half of the total curve. In other words, that's our 68%. Now, what I like to do is to break this 68% down into 2 equal parts. Remember that this curve is symmetric. This means from 1 standard deviation below the mean up until the mean is 34% of the data, and from the mean to 1 standard deviation above is also 34%. In terms of our example, this would mean 34% of the values are between 26 and 33, and 34% of the values are between 33 and 40. The next part of this rule is the 95, and the 95 says that 95% of the values live within 2 standard deviations of the mean. In other words, 95% of the data is going to be between 2 standard deviations below the mean and 2 standard deviations above. In the case of our example, this would mean 95% of the values are between 19 and 47. This is almost the entire data set. Just 5% of the values do not live in this region. This kind of makes sense. Remember that a standard deviation sort of represented an average distance from the mean. So if I am more than 2 standard deviations away from the mean, that means I am more than twice as far as average from the mean, from the average. So it makes sense that most of the values are going to live close to the mean. Then I like to break this up as I did before. So here's the orange region that we found. Each of these pieces is 34%. To figure out how much these green regions represent, we know that the total of the green was 95%. If I remove that orange piece, I can subtract 68%. And so what remains in those 2 green regions right now is 27% of the data. To find each region, I can just divide that by 2, and that'll tell me 13.5. So 13.5% of the data lives between 2 standard deviations and 1 standard deviation below the mean, and 13.5% live between 1 standard deviation and 2 standard deviations above the mean. The last part of this rule is the 99.7% portion. And you guessed it, that means 99.7% of the values live within 3 standard deviations of the mean. In other words, just 0.3%, not even 3%, but 0.3% of the values are going to be further away from the mean than 3 standard deviations. As we did before, we can split up the different segments of the normal curve. So here are the 34 and the 13.5 pieces we found before. To compute the amount in the blue regions, we can take that 99.7 and subtract the 95% to get 4.7%. So the little blue pieces on the screen is a total of 4.7% of the curve. If I cut that in half, that tells me that each blue piece is 2.35%. So each of the blue pieces represents 2.35% of the data set. In terms of our example, this means that 2.35% of the values would be between 12 and 19, and 2.35% of the values would be between 47 and 54. Now, if I wanted to know the amounts that were beyond 3 standard deviations, I would just take that 0.3% and cut it in half, and that will give me 0.15% on either end of this curve. In other words, 0.15% of the values will be below 12, and 0.15% of the values will be above 54 for our example. Please note that this is 0.15%. That doesn't mean 15, it means 0.0015. So this is a very small proportion of values in our data set. Now, what the 68, 95, 99.7% rule says is that if your distribution follows the normal curve, if it has this kind of a shape, then these percentages are going to be true no matter what your mean or your standard deviation is. In other words, there will always be that 34, 13.5, 2.35, and 0.15%. There will always be those values no matter whether our mean was 33 with a standard deviation of 7, or if the mean is 100 with a standard deviation of 20, or it doesn't even matter. No matter what your mean and your standard deviation are, as long as your distribution follows the normal curve, these percentages are going to hold true. So let's look at an example that's going to apply this rule to a normal distribution. Suppose the grades on a recent test are approximately normal with a mean of 70 and a standard deviation of 9. As soon as I see this information that the distribution is approximately normal, I'm going to draw myself a normal curve. I'll always label one tick mark in the center, and then I'm going to count 3 up and 3 down. Then to label my axis, I need to make sure that the mean goes in the center. Since the mean is 70, I'm going to write 70 in the middle of my curve. Since the standard deviation is 9, I'm going to add 9 each time to move up, and I'll subtract 9 each time to go down. In other words, 70 plus 9 will give me 79. I'll add 9 again to get an 88, and then I'll add 9 one more time to get a 97. To label the rest of the axis, now I'm going to subtract 9 each time. So 70 minus 9 is a 61. Subtract 9 again to get a 52, and subtract 9 one more time to get a 43. So whenever I have a problem that's got an approximately normal curve with a mean of a standard deviation, this will give me a good place to start. Okay, let's use those percentages that we were looking at before. Part A. Suppose a grade of 61 or higher on the test is a passing grade. What percent of the class passed? In this example, the information that's super important is that the grade of 61 or higher constitutes passing. So I'm going to diagram on my normal curve this information. I move over to the 61 and I draw a line up. Since 61 or higher is passing, the higher part tells me I should shade to the right. So that's what I do. So I'm going to shade to the right of this 61. What I need to figure out is the total amount of the shaded region. And there are a lot of different ways that you can do this, but here's what I notice. I notice that that mean of 70 is included in this shaded region. So first I'm going to draw a line up at the 70. Now remember that the mean and the median on a normal curve are the same. So that means 50% of the values are below 70 and 50% of the values are above 70. So the piece of this curve above 70 to the right of 70 is 50% of the data values. To get the total shaded region, I just have to figure out what is in that section between 61 and 70. If I think back to that curve we just drew, here were the percentages written out for us. In between the mean and one standard deviation below is 34% of the data. So that means between the 61 and the 70 is 34% of the values. This is our entire shaded region, so to figure out the percent of the class that passed, all I have to do is add up those two values. So 50 plus 34 is going to give me 84%. Thus, 84% of the class passed the test. Let's do another example. What proportion of the class earned between a 52 and a 79? To begin this example, the important numbers are the 52 and the 79. So I'm going to begin by drawing a line up at the 52 and also a line up at the 79. And we are interested in the proportion of values that are in between those two. In order to figure out the percent of values between these two numbers, first I'm going to draw lines up at the 61 and also at the 70. This is going to divide my normal curve up into those segments that we looked at earlier. When I think back to that curve, remember that these percentages are always the same. So between the mean and one standard deviation above, in other words between the 70 and the 79, is going to be 34% of the values. Then between mu and mu minus sigma, or Between 70 and 61 is another 34% of the values. And between the 52 and the 61 are going to be 13.5%. Remember that even though the mu and the sigma can change, the percentages will never change. These will always be the same. So, to figure out the proportion of values between the 52 and the 79, all I have to do is add the two 34s and the 13.5, and I end up with 81.5%. Now, in this case, we weren't asked for a percent of the class, we were asked specifically what proportion of the class. In this case, when proportion is asked, that means that we are looking for a decimal answer, not a percent answer. So we have to change that 81.5% into a decimal. You can do this either by dividing by 100 or moving the decimal point to the left 2 spaces. But either way, you'll end up with 0.815. So the proportion of the class that earned between a 52 and a 79 is 0.815. Let's do one more example of using the empirical rule together. The probability is 0.975 that the class scored below which grade? Now this question is a little bit different from the two that we looked at previously. In this case, instead of being told a grade or 2 grades and looking for a percentage of values, now we've been told a probability, which is the same thing in this case as a percentage, and we need to figure out a grade. So this is kind of backwards from the problems we've been doing. The first thing I'd like to do is change that 0.975 into a percentage. So you can do that either by multiplying by 100 or by moving the decimal point 2 spots to the right. Either way, we end up with 97.5%. So we're told that 97.5% is below some grade. We need to figure out what grade is that. Now, there are a couple of ways to approach this depending on what information you notice and how comfortable you are with your empirical rule. For example, one thing that I notice is that 97.5% is more than 50%. So, to figure out this problem, I know that this cutoff has to be beyond the halfway point. So the halfway point of my curve is at the 70. So I'm going to begin by cutting off my curve at 70. There's my 50%. Next, to figure out where my cutoff is going to be, I'm going to keep adding those segments that we found earlier until I get to a total of 97.5%. For example, the next cutoff on my curve is at the 79. So if I were to add this piece, that would be adding an additional 34% to the curve. This means that if I add those up, 50 plus 34 is 84% of the values. In other words, 84% of the class scored below a 79. Since we're looking for 97.5%, I'm not quite at the percentage I need yet. So I'm going to add on another segment. The next segment was 13.5%. So I can add that to that 84 we found earlier. So 84 plus 13.5 is 97.5%. This matches the cutoff that we're looking for. We finally got to that 97.5 percentage. And the cutoff score is going to be an 88. This means that 97.5% of the class scored below a grade of an 88 on the test. This concludes the video on the empirical rule, also known as the 68, 95, 99.7% rule. Now this module, Module 6, is going to focus primarily on the normal curve. One of the downsides to the empirical rule is that if a value is not a full number of standard deviations away from the mean, in other words, if it's like 1.5 standard deviations above or 0.2 standard deviations below the mean, the empirical rule won't help us. It only tells us information about values that are full standard deviations away from the mean. So in the next few videos, we'll be developing some techniques for dealing with values that don't fall a full standard deviation above or below the mean. You can get started by clicking on the arrow to the right and watching a video about z-scores. Or if you prefer, you can review the previous video about probability density curves by clicking on the arrow to the left. Thanks for watching and have a wonderful day.